Welcome back to the fifth video of the series Programming with RFEM6 and Python. In this video, things get exciting as we are actually going to start modeling. The example for this video is a simple cantilever beam, as shown. The first step in most coding projects is to import the libraries meaning extended functionality that we want to use. For communication with RFEM6, there are two libraries which should always be imported at the beginning of our code. These are the enumeration library, so from rfem.enums, import everything, and the model initialization, so from rfem.initModel, import everything. These are critical for us to initiate a model, and from here on out we import additional libraries according to the specific functions that we need for our structure. Note that when importing a library, the code inside these .py files is actually run, so simply by importing the init model, some communication with RFEM6 is already taking place. How we think when modeling a structure in RFEM versus programming it in Python is relatively similar, and with this notion, hopefully the process is cleared up slightly. Normally, one would open the RFEM application and create a new model. These steps are mimicked in Python by defining a model object, simply by typing in model. We have certain parameters, so a new model is true, as it is our first model, and we give it a name. For example, my model. With the model object defined, we need to make it open for modifications, and this can be done with model.clientModel.service.begin modification with the argument new. Once you're done with your work, you usually save it, and this step can be preempted in our code by ending the modifications. So model.clientModel.service.finish modification. Our model definition now comes in between these two begin modification and finish modification calls. This code can now actually be run and a model object will be created. And since we have a model object now, we can change the following parameters in line 6. So it's no longer a new model, but we are editing a existing model, so we just change the Boolean flag to false. Thinking of modeling a structure, we need to define its sections, its materials, and also its geometry and the support conditions. Then we'll add some loads, define the load cases and the load combinations, set up the analysis settings, and then finally run the analysis. Thanks to the RFEM6 libraries, this process can be quite effectively done. To define nodes, we need to import the basic node objects, so from rfem.basicobjects.node, let's import node. Having the nodes, we need to connect them with a beam, so we import the basic beam objects. Furthermore, a beam is made up of a specific section and a material, which we'll also need to import. So from rfem.basicobjects.member, import member, and we can do the same thing for section. As well as material. The structure needs to be supported, and we will do this with a nodal support. So from rfem.types for nodes, .nodal support, let's just import everything, and we will need to load the structure. Again, this will be defined on the node, so we will import the appropriate nodal loads library from rfem.loads.nodal load. And again, let's just import everything. While we add it, we need to define a load case for the load and define its analysis settings. So from rfem.loadcases and combination .load case, let's import everything. And from rfem.load cases and combinations.statical analysis settings, import everything. Here the logical breakdown in steps, just like in RFEM6, is evident. One could also open up an example file provided in the high-level function GitHub repository and simply copy all the import statements into your file. However, when starting out, it is nice to get familiar with the various libraries. We can now define the geometry of the problem. To start, we need to define two nodes, one start and one end node, just like in RFEM6. The beam's geometric location is defined between these two nodes. We call now the appropriate function to define our nodes, which is node. This is our first node, so it will receive the number 1, and we place it at the origin. We can do the same for the end node. However, we want to introduce some degree of parameterization for the length of the cantilever. In this simple example, the length of the cantilever is simply the x-coordinate of the second node. So we declare a variable L, which will be given a value by the user at runtime. This can be done with the native Python input command. Later, when we run the code, we'll be able to see the message length of cantilever in meters, and we'll be able to give the length of the cantilever in order for RFEM6 to model it. We can now use the definition of L as the x-coordinate of our second node. As mentioned, a member is made up of a section and assigned a material. We start by defining a section, and for that we call the appropriate section function. We give it a number, and we assign it a section from the database. Since this is the first section in our project, we give it the number 1. Furthermore, for our cantilever example, we will use an IPE200. By passing the string IPE200, the sectional properties are obtained from the RFEM6 database. Now we have a section, which is identified through its number 1. The same applies to defining a material. We call the material function and give it a number. We use a standard steel material, namely S235, and can access it from the database the same way we did for the IPE section, with a string. And now with this line we have defined a material number 1 with the steel properties for the class S235. Now that we have created the two nodes, we can define the member between these two nodes by simply calling the member function. By using the member function as shown, a default member is used. Using dot notation, we can however specify the member type. For the purposes of this video, a standard beam suits our purposes fine, so we leave it as is. When the doc strings appear, we can see what parameters are required. This is the first member in our project, so we give it the number 1. We want to define this member number 1 between our start node, node 1, and our end node, node 2. For that we have our next two parameters. Parameter 4 of this function is the rotation angle. We set this to a value of 0, and you can see the required types always given in the documentation. After the rotation angle comes the section assignment. This is needed at the start and end node, just like in RFEM6. We have already defined this, and is given through the number 1. Therefore, the parameter inputs 5 and 6 will get the number 1. With the geometric portion of our problem completely defined, we can define the boundary conditions, i.e. the support for the cantilever. As mentioned, when importing the libraries, this will be done through a nodal support. The nodal support function is regarded as a type for nodes and is found in the RFEM6 library under types for nodes, which is similarly represented in the import sequence. This is the first nodal support. Therefore, like with the previous geometrical entities, it gets the number 1 as the first parameter. The second parameter is the nodes to which the support attribute needs to be assigned to. Attention needs to be paid to required data type of this parameter. It requires a string, which may be surprising. However, this is because multiple nodes can have this assignment, meaning not just node 1, but for example 2, 3, and so on. Finally, the support type is fixed and can be accessed as demonstrated in the doc strings. Nodal support type dot fixed. No structural analysis is complete without some loading conditions. And here we start with defining a load case. For that, we call the function loadCase. The parameters are a loadCase number, which will be 1, and a name, which can be anything you deem appropriate. I will use the name LC1. The final parameter pertains to the self-weight, and the required parameter is a list of length 4. These parameters are the same as what we see in RFEMu 6. The first entry of the list is a boolean of true or false, and the remaining 3 list entries are factors to which gravity needs to be multiplied with. Typical self-weight load cases would therefore be true, 0, 0, 1. We, however, will neglect self-weight in this example. Therefore, the complete function is simply just false. We can now add a load under the above created load case. Among the many load types featured for modeling in RFEMu 6, we will choose the nodal load from the library loads for the example here, which is why we imported this specific library for that. We start with numbering the load, then assigning the load to the previous defined load case. Now we need to decide for which nodes we would like to add this load. Here we will add the point load only to node 2, in a similar manner for nodal support assignment. Forces act in a direction, which we also need to provide, and our load acts in the global z direction, which is the predefined value. Therefore we don't actually need to specify this. So we will skip this parameter. In order to skip the parameter, we need to explicitly state that we are now providing the magnitude. We will give the magnitude of the load, but here again, like for the length of the cantilever, we can program some flexibility where the magnitude of the force can be user defined. We declare a variable f and prompt the user to give it a value at runtime. And note that f is scaled by 1000 to convert it to newtons. This is done since that is what is expected of web services. Last but not least, we will define the static analysis settings. In the first and the second parameter inputs, we will give a number and a name to the function. For the third parameter, we will choose geometrically linear static analysis. This is the default value, therefore we don't need to explicitly state anything. Finally, we are now ready to run the analysis for our structure. For this, we add calculate all to our code. And now we can run the entire code, when the terminal window will be prompted for a length of the cantilever in meters and a force in kilonewtons. Note that the analysis is also being run in RFEMu 6. Here we can see the appropriate node numbering, member numbering, forces, and the results.